So we'll be starting off with a new chapter today, which is dislocations and strengthening mechanisms. In this chapter, we'll try to see what is the relationship between yield strength and the dislocation motion. We have already studied the chapters on defects, including dislocation. We have looked into mechanical properties also. Now, in this chapter, we'll try to relate the dislocation motion of the defects with the strength. We'll try to understand why these defects are important with regards to the strength of the material, specifically with regards to metals, and why dislocations are primarily observed in metals and alloys, and what is the difference it causes in terms of the mechanical properties of metals and alloys. Then the later half of the chapter would look into the four of these strengthening mechanisms, and the last part would be related to the effect of temperature on mechanical properties of metals and how it is related to the cold working of a material. So this is basically the outline of this chapter that we'll be looking into, starting with the relationship of plastic deformation and dislocation. It says that plastic deformation occurs by plastic shear or slip, where one plane of atoms slides over adjacent planes by defect motion or dislocations. You've already seen that when you are having a sample being stretched beyond the elastic limit, the planes were shearing on one on top of another, and this caused a permanent deformation in the material. The important thing over here is that this plastic shear or slip is basically something that requires the defect motion. If you remember this edge dislocation being present in a system, and the system is experiencing shear stress. So as the shear stress is being applied onto a material, you see that the dislocation moves one step at a time, and it ultimately creates a unit step of slip that has taken place. That means there has been a permanent plastic deformation that has taken place due to the motion of the defect itself. In other words, if you want to have plastic deformation or permanent deformation, there is a need of defect, number one, and due to the effect of shear stress, there is a need that this defect should move. So the movement of defect basically causes the plastic deformation. What is the relationship? The relationship is that if the dislocations don't move, the plastic deformation won't occur. This is a very important point, that the movement of dislocation is basically related to the plastic deformation of the material. So far, is that clear?
Yes, sir.
All right. Now, when we look into different categories of materials, we have metals that normally are in the cubic crystal system, or otherwise they follow hexagonal crystal structures. Ceramics, covalently bonded ceramics, and ionic ceramics. Covalently bonded means silicon and diamond, and for ionic ceramics, sodium chloride is the most common example. If you look at the structure, you would see that there is a sea of clouds, and where you have positive iron cores and electron cloud is surrounding these cores in the metallic system. It's a non-directional bonding. When you talk about covalent ceramics, they have directional bonding or angular bonding depending upon how the bonds are being shared. And then you have ionic ceramics in which there is positive negative charge relationship. So dislocation motion is easiest in metals. It is difficult in ceramics, whether it is ionic or covalently bonded. That's why uh, we'll come to the reason also why it is easier in dislocation motion is easier in metals and why not in ceramics. But this is the reason that ceramics are essentially brittle in nature, while metals are essentially ductile in nature because the dislocation motion is easier. And we have already learned that it is the dislocation motion that results in the plastic deformation. Why is it easier? Because metals normally have non-directional bonding and they have closed back planes and directions available. It is difficult in covalent ceramics because you have directional or angular bonding, and it is difficult in ionic ceramics because you have to avoid the positive and negative charges which exist in the neighborhood. Then dislocation moves along slip plane in slip direction perpendicular to the dislocation line. So if this is your dislocation line, the movement of dislocation is essentially perpendicular to the dislocation line. Similarly, in screw dislocation, if this is your dislocation line, the movement of the dislocation line is essentially perpendicular to the dislocation line. This movement is basically in a specific direction which is known as slip direction, and it is taking place on the plane which is known as the slip plane. So slip plane and slip direction, they are very important when you're talking about the dislocation motion. We are looking now into the deformation mechanisms. Deformation mechanisms is basically dependent upon slip system. So whenever this dislocation has to move, it has to move in a slip plane which make it easiest for the dislocation to move, or which is an easiest plane for the slippage or the movement of dislocation. What is the criteria for a slip plane? Slip planes are those planes that have wide interplanar spacing. That means the interplanar distance is largest, and they have high planar densities. That means the atoms per unit area of the plane that is highest. And the other thing is slip direction. The direction of movement, it is the direction that has the highest linear density. That means the atoms per unit direction or per unit length of that direction would be highest. So in order to have the deformation or the dislocation move, you need to have a slip system, a slip plane and slip direction. And what are the conditions for slip plane and slip direction? Slip direction, wide interplanar spacing, high planar densities for slip plane, and highest linear densities for slip direction. Now, if we have the three structures with us, face-centered cubic, body-centered cubic, and hexagonal closed back, we have taken certain planes for FCC, BCC, and for hexagonal we already know which is a closed back plane. So if we compare the atomic density per unit area, that is the planar density. These are the values that I have calculated for you. In FCC, triple one planes have the highest atomic density. In BCC, you have double one zero plane that is the highest density, and in hexagonal planes, it is very easier that the basal planes have the highest atomic density. And if we compare the distances between the planes, that is the interplanar distances, you would see again that triple one planes have the highest interplanar density, wide interplanar spacing. Similarly, body-centered cubic crystal structures have widest interplanar spacing for double one zero planes, and you don't need to calculate for hexagonal closed back planes because you already have single plane available that has the highest atomic density. Now, considering this, in FCC, triple one planes would have would get satisfy the criteria of the slip plane. Similarly, in body-centered cubic systems, double one zero planes, and in HCP crystal structures, triple zero one planes are the planes that essentially fulfill the criteria of slip plane. That means the planes on which it is easiest for the dislocation to move. Now, these are the planes. We have already looked into triple one planes, the 110 planes, and the basal planes, which are the highest or close packed planes for the three structures. These are the planes. Now, if we take the example of FCC crystal structure for a triple one plane, you essentially have three closed pack directions. That means the directions for any triple one plane, there would be three directions which would have the highest linear densities. And if you talk about a single unit cell, in this single unit cell, you could only have four triple one planes that would not be parallel to each other. So there could only be four triple one planes in this unit cell that would not be parallel to each other. And each triple one plane would have three directions which would be the directions of the highest linear densities. So essentially for an FCC system, slip occurs on triple one planes, which are the closed packed planes, in 110 directions. And for these closed packed planes, you essentially have 4 into 3, 12 slip systems for FCC. 4 because you could only have 4 triple one planes which are not parallel to each other uh, in this slip system, and each plane would have three directions that would make 12 possibilities of slippage in an FCC system. All right. Now, moving on towards the stress and
सर
dislocation motion. G.
सर लास्ट स्लाइड पे तो खोलिएगा सर आपने यहाँ पे HCP का जो आपने बताया डेंसिटी सर इसकी ज्यादा नहीं होनी चाहिए क्योंकि इसका एटॉमिक पैकिंग फैक्टर ज्यादा होता है
एटॉमिक पैकिंग फैक्टर किससे ज्यादा होता है?
सर HCP का ज्यादा नहीं होता
जस्ट गिव मी अ मिनट. जी.
जी सर सर HCP का एटॉमिक पैकिंग फैक्टर ज्यादा होता है ना बाकी दोनों से
HCP का एटॉमिक पैकिंग फैक्टर क्या होता है?
सर 68% आई थिंक सर
68% होता है बॉडी सेंटर्ड क्यूबिक का, रफली 74% होता है FCC का, एंड सिमिलरली 74% ही होता है HCP का. तो ये तो एटॉमिक
ओके
पैकिंग फैक्टर है.
ठीक
तो
ठीक सर वो कंफ्यूजन हो गई थी ठीक
stress and dislocation motion. Now, if I ask you grain or a crystal, the slip or the plastic deformation in a grain or crystal, is it due to shear stress or is it due to tensile stress?
shear stress की वजह से होगा.
All right. Or uniaxial tension, can it produce a shear stress?
सर वो तो फिर ऑब्जेक्ट उस डायरेक्शन में चला जाएगा.
जी.
वो तो सर अगर एक डायरेक्शन में आप सिर्फ टेंशन अप्लाई करते हैं तो ऑब्जेक्ट सिर्फ उस डायरेक्शन में चला जाएगा.
Can
सर
it
इसमें
produce?
एक लाइन के अक्रॉस एक ही एक्सेस के अक्रॉस अगर आप फोर्सेस अप्लाई करते हैं तो फिर shear तो नहीं प्रोड्यूस होगा.
Right. Let's see. We are basically looking into a resolved shear stress which is known as TR. we have to relate the tensile strengths applied to a single crystal so that the shear stress starts acting along the slip direction. Let's see how. Agar if we are applying a tensile stress, which is this is stress or force along this pink area, and we see that our slip plane is at an angle to this plane and it has certain direction, slip direction available. इसी सिस्टम के अंदर you have the plane which is the slip plane. This slip plane is essentially at an angle to the force that is being applied, and on this plane there is a direction which is the slip direction. Now, would there be a component of this tensile force that would be acting uh, on this plane or parallel to this plane? G. Would there be any component of the normal force that would be acting parallel to this slip plane? Are you guys there?
Yes, yes, sir. Right.
Yes, sir.
Yes, sir.
So I have asked a question.
Sir. No.
Sir, horizontal
sir.
component.
G, sorry.
Horizontal component.
Yes, sir.
Let's see. ये जो नॉर्मल फोर्स एक्ट कर रही है यहाँ पे, इसका कोई कंपोनेंट would be acting along this direction. If I want to resolve this force F onto this plane, there would be a normal component and there would be a component which would be parallel to this area, this green area. So I can resolve essentially this force which is acting in the normal direction into two components. One of the component would be perpendicular to this green area and the other would be parallel to this green area. The one that is parallel to the green area is basically known as the shear force, Fs, and it would be acting in the slip direction. Is it clear or not?
Yes, sir.
Similarly, the area on which it is acting would be at an angle to this pink area. All right. That would be the area which is the area for the shear. So the force and area, they both would be at an angle with regards to this external force, and that would be basically the resolved component of the stress that is acting in the tensile direction. Does that make sense or not? Yes,
Yes,
no.
sir.
सर ये जो ऑब्जेक्ट मतलब कि टूटेगा
जी,
वो इस मतलब कि जो आपने कहा नॉर्मल स्लिप की वजह से और दूसरा इन दोनों की वजह से टूटेगा।
अभी टूटने की बात कहाँ हो रही है? अभी तो मैंने टूटने की कोई बात नहीं की।
तो इन दोनों का क्या मतलब कि मकसद होगा सर?
अभी हम सिर्फ ये कह रहे हैं जो नॉर्मल फोर्स एक्ट कर रही है, टेंसाइल फोर्स जो ये एक्ट कर रही है, ये जो टेंसाइल फोर्स एक्ट कर रही है इस सरफेस के ऊपर, क्या इसका कोई इफेक्ट किसी एंगुलर प्लेन के ऊपर है जो कि स्लिप प्लेन और स्लिप डायरेक्शन में एक्ट कर रही हो?
यस सर।
ये जो फोर्स है इसको हम रिजॉल्व कर सकते हैं कि वो इस एंगुलर फेस के ऊपर एक्ट कर रही हो, उसको हम रिजॉल्व कर रहे हैं बेसिकली। और तरीका क्या है कि इफ आई टेक लेट्स से if this is my force which is acting on this pink area, I can essentially resolve this force into two components, or in other words, uh, this is my normal force. I can resolve the normal force into this component which is Fs and Ns if I know the angle which is lambda. This lambda is the angle between the force which is acting normally and the slip direction. Is this clear?
Yes, sir.
So Fs could essentially convert into F cos of lambda. So the normal force which is acting normally, this component F cos of lambda of this normal force is acting along the slip direction, and slip direction is dependent upon this lambda. Clear?
Yes, sir.
All right. If I talk about this area, this is my area AS. This is essentially the normal area. If I move A onto this side, this is again A. The angle between AS and A is phi. So AS or cos of phi is essentially A upon AS, and AS would essentially be equal to A divided by cos of phi, where A is this, AS is this green, and this phi is the angle between the normals of the two planes. Is it clear?
नो सर, ये दोबारा वो कर दें, ये a by a cos of phi कैसे हो? सर यहीं से डायग्राम से।
जी मैं डायग्राम से बता रहा हूँ। ऑलराइट, ये मेरा दिस इज एएस की डायरेक्शन है ये मैं आपको एंगुलर डायरेक्शन बता रहा हूँ। एएस मेरा एरिया जो है वो इस डायरेक्शन में है, ठीक है।
यस सर।
और जो ए है वो इस डायरेक्शन में है, ठीक है।
यस सर।
अच्छा, अब आप एज्यूम करें कि ये 90, दिस इज 90 डिग्री एंगल, और अगर मैं एएस को ट्रांसलेट करके इस जगह पे ले आऊं, तो दिस इज माय ए, दिस इज एएस, और इनके दरमियान जो एंगल है वो है फाई का, ठीक है।
सर
अच्छा, अब दिस इज द हाइपोटेनस which is AS, this is my base and this is the height. तो cos of phi जो है वो क्या होगा?
Sir, base over hypotenuse.
Base over hypotenuse, which is A upon AS. Is it or is it not?
यस सर।
Yes, sir.
AS को इधर ले आए, cos of phi को इधर ले आए, तो essentially AS is A over cos of phi. All right.
Yes, sir.
Yes, sir. सही है.
Yes.
Acha. Now, if I know that the shear stress or resolved stress is Fs over As. Fs is the shear force along the slip direction and As is the shear area or the plane on which area of the plane on which this force is being applied. Fs is F over F cos of lambda. A As is A over cos phi. So if I divide the two, I would essentially have F cos lambda A into cos of phi. Would this be the expression?
Yes, sir.
और ये चीज जो है F
Yes,
over
sir.
A is essentially the tensile stress or tensile load that is being applied. Clear? Yes
Yes,
or
sir.
no?
Yes, sir. Clear.
So the resolved shear stress would essentially be this is stress, which is the normal stress or the tensile stress multiplied by this factor which is representing lambda. Lambda is the angle between the normal force and the slip direction, and phi, which is the angle between the normal plane and the slip plane. Clear?
Yes, sir. Yes, sir.
All right.
Yes, sir.
All right, good. So